All right, these are homework 15 hints. So we have number 2. These are, of course, the problems. They give us the density of what is it, the cloud of interstellar gas. You know, these are clouds that are found between the stars. So the density of the cloud is equal to, what did they give us? 1.6. Well, I mean, you guys can read this, but 1.67 times 10 to the minus 20th. And of course, and the thing about this is a little bit different than densities that we've had before. Sorry, that's supposed to be 10 to the minus 20th. It's in kilograms per cubic meter. All right, so that's a little different than we're used to grams per cubic centimeter, but it's perfectly fine to use density in those units. For this particular problem, that works out really well. And so what we do is we use the density equation, right? Of course, the density equation in general is density is equal to mass divided by volume, right? And so they want us to know what they want to know what the volume of the cloud is, right? So if there's one solar mass of material there, all right. So we just rearrange this equation and solve for the volume, right? So this equation leads to the following: the volume of the cloud. So I'll just put C for the cloud. The volume of the cloud is equal to basically the volume and the density switch places. So it's going to be the mass divided by the density. And of course, you put the mass of the sun in there, right? I mean, I'm not going to do the whole problem, but you guys can do this. Of course, remember the density. I'm sorry, the mass of the sun is 2 times 10 to the 30th kilograms. Right, and then you put in you put in this density right here. You put that in the denominator. All right, so that'll get you the density of the cloud. I'm sorry, the volume of the cloud. All right, let me switch to a new one here. It's just easier than erasing the whole thing. All right, and so what you do is once you have that, now we need to know what the volume of the sun is, and that's I'll just use an S for that's the volume of the sun is the standard volume equation 4 pi over 3 times the radius raised to the third power. So you got to look up the radius of the sun, and I'll just give it to you here. So that's going to be equal, of course, 4. I guess I didn't need to write that twice, did I? 4 pi over 3. And here's the radius of the sun in meters. You want to do it in meters here because we're going to compare the volume of the sun to the volume of this cloud. Anyhow, the radius of the sun in meters is, you can look this up in the front cover of your textbook, the back of the front cover, 6.96 times 10 to the 8th, times 10 to the 8th meters, right? And then of course you have to cube that, right? And that'll give you the volume of the sun. And then the next part that they want to know is what's the ratio of the cloud's volume to the sun's volume. All right, and so this ratio here. So this is the ratio. That's an O. Sorry, that looks like an A. That looks like an A, doesn't it? So the ratio is the volume of the cloud that you already discussed, you already calculated that. So this the volume of the cloud divided by the volume of the sun, which you just calculated right here. All right. So that's just report what that value is, and then what they want to do is make it a little bit. They'd like the units of the cloud, the volume of the cloud. Okay, so this has nothing to do with the ratio. Okay, this is just another part of the problem. They want to know what is the volume of the cloud. So remember, you already have some number. You already calculated this. It's the some number. It's a very large number in cubic meters, right? Because we had calculated that in cubic meters. All right. What you have to do? They want you to change that to cubic light years. All right. And so here's how you do it. So you just need the conversion. It turns out that one light year, LY stands for light year. One light year is 9.46 times 10 to the 15th. 10 to the 15th meters. And so if you basically, if you cube the numerator and the denominator of this conversion, right, you just cube both of them. Of course, the 1 light year is just going to be 1 light year cubed, but then you cube the 9.46. Make sure that there's a decimal point there. That's supposed to be a decimal point. Sorry. 9.46 times 10 to the 15th. Cube that, and that'll give you the conversion factor. All right, let's move on to, let's see, how am I doing on time here? All right, well, I'm doing okay. All right, so let's move on to problem number 5. That one was a little bit long, all right? So here's number 5. It's just a escape velocity equation, right? So the escape velocity is, what the standard thing, the square root of 2 times g, big G, times the mass of the object divided by the radius. And this time, what they tell you is this is the I think this is a what is this? This is a planetary nebula. All right. So they give you that R in this equation, R is 100 times the radius of the sun, right? And so that's 100 times 6.96 times 10 to the 8th meters. All right, so you multiply, you multiply that, that number times 100, and of course you're going to use this value right here, and then of course for m you're going to use the mass of the sun, right? If for m, of course, just to remind you, is 2 times 10 to the 30th power of 30th kilograms. All right, so once you have that, you'll get that escape velocity. They ask you to compare that to the escape velocity for a typical planetary nebula. And so for a typical planetary nebula, here's so this is what you're comparing it to. The typical value, I don't know, I'll call it typical, right? Typical. Sorry, that didn't look very nice. Is about 20,000 meters per second. All right, so when you do this calculation up here, how does that compare to 20,000 meters per second? All right, that's number 5. Here, let me go to the next one here. All right, so for number 6, it is let's see. So for number 6, we get they give us the volume of a red giant. Well, they want us to calculate the volume of a red giant. So this I'll call RG red giant. So the volume is going to equal 4/3. Sorry, 4 times pi divided by 3. Sorry, that didn't even look like a 4. So 4 pi divided by 3, and then they give you what the radius is of the red giant, right? And of course you have to cube that. And let's see, what else do we have to do? Yeah, all right, and then so once you figure out the volume, they want you to figure out the density of the red giant. So the density, of course, of the red giant, that's supposed to be Rg, is equal to they want to use the mass of the sun, but you got to put the mass of the sun in grams, of course. Remember, the mass of the sun is 2 times 10 to the 30th kilograms, so that would be 2 times 10 to the 33rd grams divided by the volume of the red giant, right? So, and of course you just figured that out, right? You just figured out what that was by using the radius of the red giant, and then what they ultimately want to do is they want you to find. So this is separate, okay? So then they want you to find that's supposed to be a D, the density of the red giant divided by the density of the air that we breathe, and they give you the value of the density of the air, right? So the point of this is that you're going to find that the red giant is far less dense than the air that we breathe. Okay, so let's see. Let me look and see how much time I have. All right, so I might have to make this on another video actually. Here, well, let me see how much I can get done. All right, so here's number 7. Let's try to do this quickly. So for number 7, you get this equation: the velocity of something, as long as there's no acceleration, the velocity of something is the distance that the thing travels divided by the time. And so if you know the velocity and you know the distance, you could work out the amount of time. And so this equation, of course, becomes, so I'm just solving for time here. The time is equal to distance divided by velocity. All right. And this is like I think this problem is about the expansion of a red giant. So here I got about a minute left. I'll just continue this in the next video if I run out of when I run out of time. All right. So and by the way, when you do this, this is going to give you some number of seconds. All right, so just keep that in mind. It gives you the number of seconds. And so the distance that they give you is, they tell you that it's 1/4 of a light year, 1/4 of a light year. That the planetary nebula has expanded that far. And so if you look up what the distance of a light year is in kilometers, it is 9.46 times 10 to the 12th kilometers. All right, and that's what 1 light year is. One light year. All right, and so of course the light years cancel, and so you just multiply 0.25 times this number, and that'll give you the distance. All right, and that of course goes up here. All right, let's see, how am I doing on time? Oh, it's about to run out of time. All right, I'll continue this in the next video.